Hi, thanks for the invitation as well and the opportunity to reflect a little bit on this work. My background is mixed, is in mathematics education and applied artificial intelligence in education in particular. So I'm usually interested in designing environments that particularly provide feedback to students as they're working with those. And in the context of the intrapersonal network, I think the interest and overlap relates mostly to what I'm going to talk about, the affective aware support that we're trying to provide to learners as they're working with systems. We've been doing work on this area for a while, but I'll focus on a particular project that kind of exemplifies it, is the Talk2Learn European funded project. Had 7, 8 partners, but these 3 partners in particular and the colleagues that you see here were instrumental to the results I'm presenting today. Generally, the project, as I said, was funded by the European Union. There were 4 universities and 3 commercial partners, and the objectives was mostly to design an adaptive support environment and to investigate more how this can be done with a threefold approach through machine learning from large-scale data, with the opportunity of switching between structured and exploratory activities, about which I'll explain a little bit more what we mean in a minute, and taking cues from learners as they're talking online with the system, which is where the project takes its name, because the idea was that because of the fact that speech recognition is getting ground and can be applied more recently, it can, maybe we have some evidence from other work in the area that it can act as a natural interface for the students, and this could be beneficial, especially for young learners who can't maybe interface with typing, for example, so much, and that they wouldn't have mastered the written language in particular areas, but also the opportunity that speech recognition provides to infer affective states. And we chose as an application domain fractions, particularly age 12 to 12, because we know of the importance of fractions in relation to the rest of the mathematical ability, and because we had some previous content that we can build on. So in relation to the second objective, the switching between instruction and exploratory activities, most of the state-of-the-art on intelligent tutoring systems in general, and also the variety of the applications that have been developed are focusing on procedural learning. So you can see here the 2 systems that we had kind of as a background for the project, the fractions tutor, which is an adaptation of the cognitive tutors type of work that is happening a lot in Carnegie Mellon, that maybe some of you are aware about, and the WOZ tutoring system, which is a London-based company that has developed a tutoring system that is focusing on primary mathematics in particular, but because of the constraints of the technology and in general how things have evolved in the area, most of the work, as I mentioned, focuses on what we call more structured activities, where the answer might be just usually one answer, or some specific question that is very easy to check its correctness. So for example, here it would be the students would have to click one of these choices. So it just makes it so, from a technical point of view, it also makes it easier to check, obviously, the answer. What we were interested to do here start bringing more conceptual learning into the picture. And we know from our work also that exploratory learning environments have this potential as well, and because they focus on that. So in the project we designed from scratch an environment that is more open-ended, it's more interactive. What the students have to do is more like a game, but we don't call it a game because it doesn't have this game element like some of the examples you saw early in the morning, but it's more open-ended and interactive. And to give you an example here, the task the students would have to do would be to drag and drop various fractions, representations, and so on that are engaged with, and answer a question. The example here would be find a different combination of fractions that would be less than 2/10. So, and you start with a blank canvas. You would drag and drop some of these features. I don't want to go too much into the environment. Design the various fractions you are engaging with, and use the affordance of the environment to demonstrate your learning with the task. So with we designed several tasks in this environment that are more open-ended, and wanted to combine them with the structured ones. So I'll go briefly through the whole background sort of the project and focus more on how, on top of this environment, we provide feedback to the students as they're working with the environment using information that relate to their affective state. But I'll try to give you a holistic picture first of how the whole environment operates and its adaptive features. So the main engine behind the system is a kind of a sequencing engine, but I wouldn't have time to go into a lot of the detail of it, but mainly it's a kind of a flow chart. You can think about it as it's an intervention model that provides some instructional support based on some decisions that we took based on the theory, some previous empirical evidence, and so on. Tom was mentioning before the blocked practice effect, so it kind of takes this sort of things into account. We would start with, we also know from other work in the field, for example, Manu Kapu's work on productive failure, that it might be better to start with conceptual learning activities first, and some of the work in the mathematics education field would support that. So, as an example here, you would start first with the exploratory tasks. I don't know if you can see back there, but these are these blue tasks. And depending on the interaction with the environment and some inference that the system is doing on whether you're finding it challenging or not, you would continue to more structured tasks that were designed particularly to focus on misconceptions you would have on the exploratory task. And again, depending on how you find these structured tasks and whether they're challenging or not, there will be a period of a blocked practice with these structured tasks on a particular concept. You can go back to this if you're interested later. While you're on the exploratory task and you're undertaking the activity, you would get feedback. I explained the type of feedback, but that's how it would appear. It pops up as a prompt as you're working, and the system would also read it. In fact, just realized this is an old version. It also had a robot that makes it look a little bit nicer. So the here you can see one example of the task. Says make a fraction that equals 3/4 and has 12 as a denominator. So it would start from a blank canvas, and the student has to build this task. As they're doing it, the system provides both support in terms of the actions, the problem solving that the student is doing, and a more general feedback. The example here is use this partition tool. What do you notice? Can you make a denominator of 12? This is something because the system would have detected that the student is not using a particular tool of the environment that partitions the fractions. So, going back to what I keep kind of alluding to in relation to the affective states of the students, what's the relationship of our work and that? Basically, we know that the learning process includes positive and negative affective states, to just put it very general, and there is a lot of evidence in the field in relation to this and how the affector can be positive for learning. So we wanted to explore more how appropriate feedback can also help students kind of both regulate their emotions, but also use them to their advantage to respond to the tasks that they have. So the feedback we designed in the system is both what we call task-dependent support and task-independent support. The task-dependent support focuses a lot on the problem that you have at hand. So for every task, there is a set of rules that are going on and an expert system that, as you are working with the system, provides support on the task. The examples here would be, again, like, have you changed the numerator or denominator? Remember that the denominator is the bottom part of the fraction. Focusing on particular misconceptions that students have. And the task-dependent support also has a gradual specificity, reaching to a very didactic kind of hint that would say, check that the denominator in your fraction, not the numerator, is 12. So it would give a very specific hint at the end. Again, I'd need the whole talk just to talk about the task-dependent support, so I'm kind of skimming through that. So our emphasis is on this second type of support, the task-independent support, that tries to provide feedback that relates to the way the students are working and to the detected affect that is provided by the speech recognition software that we had integrated. So it would say things like, well done, you've worked hard on this task, why did you use this method? And that would be a reflective prompt at the end of the task where students would have to reflect back at what they've done, talking aloud, which we also know can be conducive to learning. This is quite tricky. What is the task asking you to do? Kind of helping them to go back to the task if they were lost. Please explain that again using the words denominator and numerator. That's again a reflective prompt. Are you finding this too easy? And so on. So these are other feedback types that we use in the design of the activity. So I'm going to talk about two aspects of the work we've done. One is the initial phase, which is required for the design of the system, and then the evaluation. For the design of the system, we have a particular challenge in that this area is kind of uncharted territory, and although there is a lot of kind of intuition, theory, and expertise in the field about how to support students, it's not necessarily easily operationalized. So one particular methodology that we use to help us design systems in the field of artificial intelligence and to train them is to collect data from a realistic situation. But there's this conundrum that in order to do that, we have to find a way first to collect the data. And then in order to collect the data, you would have to have already the system that would allow you to do that. So I don't know how many of you know there is this particular methodology. It's called Wizard of WOZ. No? Okay, so I'll say a little bit about that first. So the Wizard of Oz methodology is used particularly in the human-computer interaction field when you're designing intelligent systems in general, where you're basically pretending that the system is working in order to allow you to not have to implement the system first and explore how it's working. So for example, we have several questions here that we don't know from the beginning. We don't know whether the speech recognition system can indeed provide any useful evidence for affect detection. So how can we can't wait for months to develop that first and then start exploring what this would mean in practice. So what you would tend to do when you're designing intelligent systems is to find a way to replace the intelligent part with the human part that would not be evident necessarily to the user. So again, this is used a lot in the when you're trying to design early systems. And in our case, what we had to do is simulate particularly the speech recognition aspect that would be hard to develop, and the detection of the affect and how do we give feedback. So I'll just show a little bit more of that and see if it makes sense. So the way it's usually set up is that students will be working in one room or in some concealed area or behind a mirror or something. As you may have guessed, the Wizard of Oz methodology takes the name from the Wizard of Oz story that should have mentioned that Dorothy discovers that basically there was no, that the wizard was just a simple man basically giving any random advice that he would come up with. So what we do here is as the students are working here, there's someone at the behind who they can't necessarily see, or maybe in other cases it would be completely hidden, that's able to observe the student interaction and provide feedback as they're working with the system. In our case, the way we set it up was that students are working with the environment. They have a speech microphone, and the microphone is connected to the wizard, who can hear what the students are saying, but the students don't know that. They think they're working with the system. The wizard can also see the screen of the students, so the students can't be affected by the wizard kind of looking over the shoulder and so on. And the wizard has some additional tools by which they can provide feedback to the students directly. It doesn't matter how exactly they're connected, but another computer of the wizard can send messages to the students. What we did here in particular, which is was quite challenging to set up, was that we were really interested in setting it up in an ecologically valid way, because usually these studies are done in controlled environments or in a lab where you would have a mirror or something like that. And we did our pilots in very controlled environments, but we noticed how it was affecting students a lot, particularly in relation to how and whether they're talking to the system. Because it's very different if you are alone with the system and maybe there's a researcher nearby, or with another student and you're talking to the system, or you're completely alone. So what we did was to set up the environment the way you saw in the picture earlier. That is this island in the middle of the class, and two students are working simultaneously with the system. Another 10 or so are working with the computers that are around the lab, the ICT room, and the whole thing is presented as a proper ICT session from the school. So all the students are doing the same. The ones that are talking with the system and nothing necessarily happens with their interaction. They tend to kind of stop talking with it. The others in the middle get supported by the wizard. It's not obviously possible to support 10 students simultaneously. We did this in various settings and reached up to 4 students being supported by 2 wizards at one time, but it's quite challenging on its own right. But it's one way that we bootstrap this whole process that otherwise would have been impossible. So again, we're interested both in kind of understanding the interaction possibilities of this environment, and also start answering some research questions to get evidence on whether this is worth doing. And third, collecting the data to be able to train the system. So in order to do that, in early pilots, we designed the possible interventions that the wizards do. And then we come up with a particular script that they need to follow. They get trained on that in order to simulate the behavior of the system, because obviously a human has much more access to multimodal cues, and the system won't necessarily have that. So we're trying to limit the kind of interaction capacity that a human has in how they're responding by training them on this particular script that they have to go through. And in order, again, to simulate the behavior of the system, they copy-paste feedback from the from a document, basically, in a screen, which is then read back to the students. So the students never understand that, again, it's a human sending them the feedback, particularly because it's read by the computer. In earlier iterations, we allowed the wizard to type the feedback, but obviously this takes time, and then by the time the student gets some feedback, it's 2 minutes later, and this is completely unnatural. So, so we introduced this situation, and at the same time, as I mentioned, we're interested in observing what is the response of the students to this, and particularly in relation to their affective states. So again, there we have a couple of ways of how to have the sort of ground truth on their affective states. And the most typical one is doing some annotation on either on the fly or retrospective. We tried various versions. The student screen display and their voices were recorded. Obviously, this leads into a lot of video data that's hard to analyze. 2 researchers annotated the affective states and then had a discussion in the places where they have disagreement. We focus on this particular subset of affective states: enjoyment, surprise, frustration, and boredom, and confusion, which has been shown particularly to be quite interesting depending on how you interpret what confusion is, in that it has the potential to contribute to learning in particular instances where the students are confused. So with this in mind, there's a particular methodology introduced by some colleagues in the States called BROMP, based on the acronym of the names, in which observers are working in the classroom as the students are interacting with the system, and they have access to the whole body posture and interaction and speech of the students as they're working, and an app that they're using on a phone to annotate the affective state at a particular instance and time point. So, so we're following this particular methodology, and in the meantime, and that methodology we also, you'll see later on, we're using it also in large classes when we design the system in order to test it later. But still in this wizard of WOZ settings, of course, compared to the earlier studies, this generates very small amounts of data and possibilities of doing wizard of WOZ experiments with the students. But because we're looking at the level of feedback provision, the transactions are much more. So we have this about 400 messages that were sent to these students, and this is the distribution of the various types of feedback that the wizards chose to provide as the student is working with the system. So what we're interested in doing from that, at the very minimum, this helps us train the system, as I'll explain in a minute. But we can also explore it, to start observing things that would affect the design of the system itself. So one particular aspect that we're interested in is the transitions between the affective states of the students based on the types of feedback that were provided. Because again, going back to both theory and expertise, it is not clear how you can manipulate sort of the or intervene in the affective state of students based on the feedback. So looking particularly at confusion, we can look at how this has been affected. So this is a kind of transition from confusion to different affective states as the colors show at the bottom. So I don't know if it's easy to notice, but particularly the affect boosts and the instructive feedback have led students to go from this confused state that they were to a more in-flow state with the system. So they were more engaged in kind of taking actions that would be in line with the problem they have to solve. But so instructive feedback were this type of exams that I showed before, where we're really giving a specific kind of instruction about what to do and how you can get out of this confusion. But this other problem-solving support was more of a guidance type of feedback that is a little bit less descriptive and specific. And you can see that there are less changes from flow to from confusion to flow. Like students still stayed in this confused state. So this begins to tell us something about how we can design the system to provide more instructive feedback when it detects that students are in this confused state. We're also more particularly interested in frustration, because frustration is a negative state and has been shown to negatively correlate with learning. So again, here we would, you can see these affect boosts that we designed, that they had this effect of taking students out of frustration to either flow or confusion, which at least is interpreted in a positive way. If you get out of frustration to confusion, then it's a more, not necessarily from the student point of view, but from a learning point of view, it's a more positive state. So I'll get to the proper evaluation later on, but we did these studies mostly as an exploration of the area. And as I said, the way to train the system. Well, you can see that we are beginning to have some insights in relation to affective states and feedback. So, and how important it is to pay attention to this factor that is not very well understood. So, again, well, these are the findings I just mentioned. But there are other variations that we have tried as well. For example, the feedback can be presented as a pop-up, or it can be presented as a something that the students can access by clicking a button without interrupting them. And there again, the low interactive feedback might be preferred by the students when they're in flow, like they don't like the interruption. But sometimes it's really needed, especially when you are confused or especially frustrated because you don't even realize that you're kind of getting lost by what you're doing there. So with this in mind, with the data we collected, we trained the dynamic Bayesian network, which, again, I don't want to go too much into the detail here, but the point is to using all these transactions from feedback provided and the relation to the affective state. We want to predict whether you'll get from a negative state to a positive state, or what we call this enhanced state, because we also treat as enhanced the frustration to confusion state, although this is debatable whether it's a negative or a positive state. But this transition, we think it's quite is a positive. So based on the detected affect, the feedback, and whether it has been followed, and the feedback type, we train a network to be able to predict the affective state. So we implemented this in the system, combining with all the other components of the system, particularly the speech recognition component, and designed the whole intervention that we wanted to test in a bigger study. So kind of moving on and going beyond this wizard of WOZ type of experiments that are quite small, and although allow the data collection process and the training of the system, we want to start understanding the effect of this. So we did two rather big studies, one in England and another in Germany, where had different research questions and hypotheses and so on that we wanted to test. We developed this experimental design where varied whether the system has the speech functionality on or off, because we're interested in seeing whether the speech recognition component can enhance the whole learning, or it had the exploratory learning environment on and off. We focused on these three conditions, mostly because of resource limitations. And these were the participants in the two countries and the number of students that completed the study. In terms of the dependent measures, we had a pre and post test with fractions problems, 3 procedural and 3 conceptual items, and some offline paper tests that were also followed up with interviews. We haven't looked at this data in detail yet because too much. These are the type of items. So the students would complete before the intervention. They would do a pre-test, and after the intervention. At the same time, after every task, we would ask the students to self-report. And here, at the top part, they would report on how they found the task, okay, difficult or easy. And at the bottom part, whether they thought it was interesting, confusing, enjoyable, frustrating, something else, or I don't know, or the possible answers. So that we combine with other data as well, since we were doing the study, and different people across UK and Germany were interested in different aspects. So we have attitudes to learning, mathematics and fractions in particular, the user experience overall, like whether they like the platform and so on. The affect observations, the way I mentioned before, with the people walking around and annotating the student affect, and the self-reports, the interaction, and some interviews. The procedure was as follows. There were 10 minutes of the introduction, the pre-test, the intervention, and the post-test. We have two key hypotheses. One is in relation to combining the structure and the exploratory tasks, and the other in relation to the speech. I won't focus on the first one, because again that would be a talk on its own, but just as a teaser, and my particular interest was also on this combination effect in relation to combining the structure and the exploratory. And we have seen that there is a clear evidence of the improvement between the two platforms. So that's a condition 1 and condition 3, where we didn't have the exploratory environment. And we can see a clear statistical difference. So it's quite interesting. If you are interested in that, there is a CLS paper that is coming out. In relation to the speech, we get more mixed results. And actually, that's the area where we'd like to do also more analysis and go also in relation to the self-reports data and see how we can combine all of this together. There seems to be some tendency in relation to learning. The results are not statistically significant, but we have kind of moderate effects. And but in the hypothesis, we don't have only our hypotheses are not only about the learning gains, because we know, particularly in relation to the whole setup, that it would be very difficult to observe this increased learning gains on these conditions, and particularly just with the speech component introduced. We know it doesn't necessarily, we didn't necessarily expect that we would find difference. So this is actually a happy finding, kind of. But we are interested in the kind of the more holistic experience that the students are having with the system and their interpretation of what's happening, as well as the more deeper conceptual knowledge that is developed when you verbalize your thinking. So, as I mentioned, so we're trying to combine the data from the self-reports, which we haven't looked yet, and the annotation of the affective states. In relation to the annotation of the affective states, this is very recent findings. These are the differences between the condition that has the speech and affect feedback and the condition 2 that doesn't. So from the observations of the annotators, we can see a clear difference between both the board but also the flow of the students. The board one, it just happens to be significant, so that's quite interesting. And additionally, in relation to the interaction of the systems, of the students, the findings suggest that the students that are in the condition that has the speech component and the affective provision on top of that, they are less off task, which we kind of expected anyway, but it's interesting to be that we observe that more explicitly. So the conclusion from that so far, at least from a technical perspective, is that the task-independent support component is able to provide some feedback that relates to the affective states of the students, whether these are correct or not, and modify the feedback that it provides. And that seems to have a kind of a positive effect on the students' learning experience. But particularly this off-task behavior and boredom that we know it's indirectly correlated with learning. And we don't have any strong evidence to report that, but we are observing some tendencies in the responses of the students in relation to how they like the platform overall and how they think about learning fractions and mathematics in general and fractions in particular. So it's an interesting thing to try to investigate this a little bit more. So as ongoing work, we're interested in start developing more hypotheses from the data we have collected, because it's quite, they're quite small in terms of having very strong statistical effects, but I think they're acting as a way of developing further hypotheses, particularly the self-report against the annotations, where we have, so that's, first of all, this is kind of a technical challenge of how do you combine the annotations of the observers as they were working around the room with the self-reports of the students. Additionally, in relation to self-reports, we have an additional challenge that we observed kind of mid-study that has to do with the interpretation of the states from the students themselves. So for some students, confusion or frustration might mean something completely different than other students. Additionally, we've developed this hypothesis that I think might be of interest to some of you, that some students are better at what I would call, and some others in the field are calling meta-affective, meta-affectivity, where they are more aware of the fact that they might be frustrated, or that they might get frustrated during a learning session, and they have the ability to self kind of recover without a necessary intervention. So if retrospectively, if we were to do this study again, I think it would be interesting to try to separate these two groups in relation to how they are reporting their affect afterwards, because I think this is conflating the results. We have a particular task that is adapted to scaffold the difficulty, and we observed a very big difference in relation to how the students reported whether they enjoyed it or not. So it's interesting, and again, it's just a hypothesis for me, that the students mostly, there is a big difference between the conditions, whether they enjoyed the platform, they all did. But when it was more difficult, they would generally report that they enjoyed it less, which it's not a problem necessarily. They still enjoyed it, so that's fine. They enjoyed it less because it was more challenging, and it challenged them more. So, and they're not so aware to be able to report that. But this particular task that scaffolded their difficulty allowed them to even understand maybe that they're enjoying it more. So I'll leave it to that. If you have any questions or something to discuss.
Thank you, Manolis. Fascinating work. Questions, comments, queries? Here comes the microphone. There, Rebecca.
Thank you. That was really interesting. I was just wondering about when you're coding the affect, and obviously you're using observers at the moment, whether you'd considered using something like sentiment analysis or some automated coding that would allow you to kind of scale up the whole process, or if that's just not part of what you're hoping to do.
It wasn't part of this, but also you mean sentiment analysis or more automated on the language of the students?
Yeah, yeah.
So that's what, partially, that's what the system does in the full-blown platform condition when the students are talking. Maybe I wasn't clear about that, but the speech recognition component can understand pitch and different keywords from what the students are saying, and it uses this to detect affect. But this is again trained from previous data. So you kind of it's a self-fulfilling prophecy kind of. So that's why we're adding this annotation methodology as a ground truth to what's happening. Now, in terms of scaling it up, This methodology of working around the classroom and not annotating videos or something like that is the closest approximation to scaling it up that we can find.
Yeah,
So.
yeah. No, that's really helpful, thank you.
In the same vein, I don't know if you're a believer in facial expression recognition technology. Yeah. That would be a possibility in scaling up. Have you investigated that at all?
A little bit. I haven't done anything in particular. One of our collaborators, should have mentioned him here actually, they're in Mexico. They've done a lot of work on face recognition. They integrated the platform and the face recognition component, and they're doing some studies, I think, September onwards. So it would be interesting to see what we find. But again, it's the same answer. I think I'm interested in how you would be able to triangulate the results, and then we can match the self-reports, the reports from the annotators, and any extra kind of data that come from sensors.
Yeah, I think the technology is rapidly improving. We looked at it maybe 2 years ago, and it promised probably more than it delivered.
Very interesting. We're also thinking about adaptive feedback, but at the same time, the whole approach you propose here is quite complicated.
Yeah. Yes.
So I look for simpler ways, and I suppose now you just have your task and then ask just some icons where children can indicate their affective states. So they can say, I'm bored, or I'm frustrated, or I'm mad, or whatever. And use that as the basis for the adaptive feedback. It's much simpler, of course, and I see, but I look for simple solutions.
No, I mean,
what would you think of such a solution?
Yeah. Depends again where you're coming from. I think the main question here was whether we're able to do that. So, fair enough. It's quite complicated, and also the voice recognition. I think it still needs some work to get to the level of accuracy that would allow full integration of it. Regardless, for a simpler solution, this was mostly the reason we introduced the self-reports as an attempt to see what happens. In previous data I have collected from self-reports years ago, I have a bit of an issue with how you would trust the results against maybe the pragmatic sort of. But this doesn't mean that from a practical point of view, I think it can be used as a simple approach, especially if you're thinking of something which is online, or it's a practical activity. I think it's not so, from a research point of view, it's quite, it's interesting after to see whether the reports of the students match reality, or what do they mean, because one of the issues with this kind of system is that students game the system, and so if there is some relationship of how they're answering with what happens afterwards, you might start observing some gaming effects, going back to the fact that they think they're not enjoying something when it's challenging, but we know that maybe they have to at least answer the task, even if you're not enjoying it. So you might observe some of these